Got it. So if you're subscribed to my YouTube, you should be getting a notification that I am going live, which is not a bad thing. Let's press this. We need to go here. Yeah, I got my notification done. Let me get the student really quickly. Let me hit save so I don't lose my work. And I'm going to share content. I'm going to share my screen. Start the broadcast. Okay. And we're going to hop over here. Let's see. So we're at the end of week 4. We did the best we could with 2.1 and 2.2. So today we're going to work on 2.3. If you know you have brothers or sisters in the waiting room, just let me know. I'll try to check back periodically, like in about 5 or 6 minutes. But I did kind of want to go ahead and get started. Now, when I looked at section 2.3 homework, it didn't seem like it was that many questions, right? So section 2.3 are on derivatives of natural log function. So express, we have the log base b of m over n as a difference of logs, right? So we have properties of logs. Let me check one thing really quickly. Okay. Oh, he popped in and out, I think. Attendance. This one. Today. Oh, are they starting? Is it time for them to do the workout? It must be. Let me see. Are we starting class? Yeah, it must be time for them to do the workout. I think I got that student already. Okay. Let me check the chat really quickly. I'm gonna leave this as it is. Yeah, okay, so that's a good question. So a question popped up asking, if we're not up to date on the homework, can we access the exam? So let me let me say that again for our YouTube audience. So this is the end of week 4. Our exam 1, we can anticipate it at the start of week 6, right? So the main thing that I want everybody to be aware of, in order to access the exam, there are prerequisites. The prereqs for the exam, I think I said it you got to score 50% on the corresponding quizzes, right? So if exam 1 is released during week 6, that means weeks 1 through 5, you need to score at least 50% on those corresponding quizzes. But in order to access each quiz, I think I've set a prerequisite that you need to score 50% on the corresponding homework, right? For instance, if you look at this week, we go through 4 different sections. Now, I just glanced at section 2.3. Let's see if I can hop over there. This section only has, can I pull it up? There it is. This one only has 7 questions, right? So 4 questions correct, and this one you're done. But there are four sections in this entire week, right? So what I did is I just tried to cut, whenever we had 4 sections in a week, I cut the amount of work that I wanted to assign, I just cut it in half, right? Because I feel like that's a reasonable accommodation or compromise or whatever. Since we're going through so many sections, I'll dial back on the amount of work that you're responsible for. I'm not trying to bombard you. I just want to touch on these topics because we're trying to get through four chapters in the time that we have, right? Hopefully that answered your question. Let me let the student in. I'm gonna hop back over here. Let me see. I think this student right here. Go ahead. And if you have a question, feel free to just unmute yourself and we can talk about it. Let me hit save. I don't lose my work. Come on. Record attendance. Like Starfish is fine. It just takes so long to open up the attendance. And I like to edit it. And like if I don't hit save, I can lose my work. So that's why I'm constantly saving. Okay, I'm gonna leave it right there. Okay. So hopefully that's the main thing, is just you want to be positioned to be ready for the exam once it's released. You don't want to be wasting time, on that other stuff. Really, the homework and quizzes are there for, the real intent is like it's practice and it's there to prepare you for the exams. The bulk of your grade from our experience is going to come from our exams, okay? So with this question, it says express the log base b of m over n as a difference of logs. So we have these properties for logs. One of them, this is like the quotient rule. The log of a quotient can be rewritten as the difference of the logs. So the log of the quotient is the same as the difference of the logs. So we can rewrite this as the log base b of m minus log base b of n. So I think the only one that does that properly is b. Right? So the log of the quotient becomes the difference of the log. So we're going to go with b and check the answer. Next question. Take the derivative. Let me think. Okay. Let me. I feel like we didn't talk about that, but let's take some time to talk about these things. Because I know we did the derivative of exponential, but we did last time we did the derivative of exponential with the natural base e. So then when you but this isn't an exponential. Okay. So yeah. Let me get a copy of this. Just need it. Because I was definitely about to launch into the derivative of exponential when it's like a not the base e. It's similar to base e, it's just one other change. Incorporate. Right here. And let's drop this here. And then I finally got a student earlier. So with my college algebra students, and they were working on the exam, one student finally asked about, just a question, he couldn't get it right. And so we kind of worked our way through it. And I gave him some pointers, going forward on how to work on these things. Okay. So here, differentiate. Now I'm going to use the quotient rule. I started to rewrite it, but I feel like the quotient rule might be the simplest way to approach this one. Okay. So the quotient rule is the low D high minus high D low over low low, right? So F prime low, which is going to be this, D high, so the derivative of x is just 1. So low D high minus high, which is this, D low. So the derivative of the denominator, the exponent comes down, subtract 1, it becomes this, and the derivative of a constant is 0. So low D high minus high D low all over low low, all right? So that's going to be this, x to the minus 1 plus 6 quantity squared, all right? And again, just stop me if I'm going too fast or if you want to talk about something else or anything like that. Just stop me if anything is not clear. Okay, so let's see if we can simplify this. We can't get any cancellations. Let me see. Because we got that, okay, over here we got a double negative, right? So this negative is gonna cancel with that. We're gonna have x over x squared, so that's gonna finish as basically x to the minus 1. Okay, so let's account for these changes. So what we're gonna have x to the minus 1 plus 6 plus another x to the minus 1 over x to the minus 1 plus 6 quantity squared, okay? I think those are like terms, and so we can add those together, okay? So here, we can get 2x to the minus 1 plus 6 over x to the minus 1 plus 6 quantity squared, okay? I'm hesitant about leaving a negative exponent. I feel like it's going to be okay. Before I submit this result, what I'm going to do is go to the question help. Style like this. I'm going to check the question help and see how do they submit their final result, right? And then I'm just going to match. So if we go first, let me check Zoom really quickly. Check my waiting room. Okay, the waiting room looks clear. Chat looks clear. So then let's go here. And let's go to view an example. Now, another thing I just want to bring to everyone's attention, say you're working through the homework and you get stuck, you team up with your classmates or a tutor and you get stuck. Don't hesitate to make use of the Ask My Instructor. What that'll do is it'll send me a screenshot of the very question you're working on with your numbers. It'll send it to my email. And if I don't respond before we meet again, then at least we'll have it on record, and we can pull it up and talk about it if you just never figure it out. Okay, so what I want to do, I want to go to view an example, it says 8 parts. What I'm going to do is just kind of go to the end, right? They're doing the quotient rule. So low D high minus high D low, that's what they're doing. And I just want to see how did they submit their final answer. And as long as it looks similar to what we have, then, you know, because we could go a little bit further, but sometimes we don't need to do all that. Okay, so they did, okay, so it looks like they expanded the denominator and they did not leave any negative exponents. That's what I was thinking. Okay. So let's take ours a little bit further because of that. So let's just get rid of this. So now, okay. So first, let's expand this denominator. So then x to the minus 1 squared becomes x to the minus 2 squared plus 12 x to the minus 1 plus 36, right? It's just squaring a binomial. And then the top is 2x to the minus 1 plus 6. So these negative exponents are really fractions, right? So these are complex fractions, right? Because we have fractions within fractions. That's the definition of a complex fraction. When you have a fraction in either the numerator or the denominator of another fraction. So I say that because in order to basically, you know, whenever you have a complex fraction, one technique is you can multiply the numerator and then you can multiply by 1 in the form of the LCD over the LCD of all the denominators, right? So if you look at all your denominators, you find the is it least common denominator, least common multiple? Yeah, least common multiple, right? Because what we're going to do is multiply by 1 in the form of the LCM over the LCM. Because when you do that, they're going to cancel out your fractions, right? So for instance, what I mean is, if we look at the denominators, keep in mind this one is 2 over x. This one is 1 over x squared, right? So if we want to cancel out all those fractions, we can multiply by 1 in the form of, I'm going to multiply the top and the bottom by x squared over x squared, right? So I'm multiplying by 1 doesn't change the answer. It just manipulates the form into, it manipulates the expression into a form that we can use, right? So then if we do this, the following happens. On top, we can distribute that x squared, right? And same thing on the bottom. We can distribute that x squared, okay? Now I'm gonna work from the bottom. So then x, let me see, x squared over x squared is a 1, so that's essentially a 1 there. X squared divided by x is just x, so that's going to be plus 12x, and then plus 36x squared. And then on top, x squared over x is just what, 2x plus 6x squared, okay? Let me see. Can we factor that? Is that a perfect square binomial? 6x plus 1 squared? Can we get a 6x plus 1 there? No. I was doing that hoping that something would cancel, but I don't think anything is going to cancel. I think the bottom is a perfect square trinomial, but I don't think anything cancels. So I'm going to go with this, and I'm going to check one other thing before I submit it. You know, we could rewrite it a little bit, but nothing cancels. So what I'm going to do is go back here. I'm going to view an example one more time. I want to see if they finish with like a perfect square trinomial or something like that. But because it didn't cancel, did they not go any? Did they not simplify it any further? One part remaining. Okay. Yeah. Okay. So they did. Okay. So they said either one, right? Because they got the perfect square trinomial. You can either write it in expanded form or factored form. But since nothing cancels, right? We're okay. I think I'm going to put mine in factored form. That's just what I want to do. Okay, so we're gonna go like this, right here, okay? Let's see. Now, if I'm gonna do this in factored form, the top I can factor out a 2x, right? I'm gonna say parentheses. Now, if we factor out a 2x, we're going to be left with 3x plus 1. Okay, that's the top. And then the bottom, we said it was what, 6x plus 1 squared? So we said it's 6x plus 1 quantity squared. Okay, let's see. 6 times 6 is 36, x squared, 12x, right? And plus 1. Okay, I feel good about this. I'm going to go with it. Submit. God is good, right? All right. I feel like we're okay. Let me just check Zoom really quickly to see if we have any stragglers. It doesn't look like anybody's in the waiting room, and I think the chat is clear. Let's go on to the next one. All right. Next question. We can suppress this. Differentiate. Okay. So this is kind of incorporating some of the things we talked about last class. Let me get a copy. And we want to take it from here. I like to include like the question ID and a copy of the original question. Again, all these things that you see me writing, I do load copies on our Blackboard page, right? You can access the reading from Blackboard, right? You can get a copy of it from everything from the beginning, anything that you see me writing, basically. All right. All right, all right. My man, my man. Okay. Differentiate. Okay. Let's try you at the top. Let's see how we feel about that. I'm gonna put you there and expand you back. Okay, I'm okay with that for now. Differentiate. Okay. So when we go to find f prime, right? The first term, the derivative of x cubed is what? 3x squared, right? 3x squared. So then the second term, the constant, you can just put it in front of your answer, right? So the 7 just kind of carries. The derivative of exponential base e is itself times the derivative of the exponent, right? So we got to say e to the power 4x, and then times the derivative of 4x is just 4, right? And then 7 times 4 is 28. And I think that's it for that one. I'm just going to go with, well, I'm going to go ahead and write it one more time. So then 3x squared minus 28e to the power 4x. All right, paste. Okay. So now what we're going to do, stop back here. This, that looks good. And we got 3x squared minus 28e to the power 4x. Okay.
Professor,
Go ahead.
how'd you get that 20? Like, why did you get 4 at the end in the parentheses?
Okay.
28.
So I think last time when we talked about, so I feel like this first term x cubed is fine, right? We've done that. That one is pretty straightforward. The exponent comes down and we subtract 1, so that's where this came from, right? So then with the second term, there's negative 7e to the 4x, right? So whenever you have a constant, you can just bring that in front, right? So the constant, I just kind of brought it down. And then the derivative of e is itself times the derivative of the exponent. So that's where that 4 came from.
You said that one more time?
Let me say it one more time. So the derivative of e is itself
Right.
times the derivative of the exponent. So that's where the 4 came from.
Okay. Oh, so whatever number is before that x, that's going to always be in the parentheses?
You gotta take the derivative of the exponent by itself, and whatever answer it, that's what goes in the parentheses.
Oh, okay.
Yeah.
That makes so much.
Yeah. So let's try. Let's see, how do we do? Oh, we got it. Okay. All right. Let's go to the next one. Let me see the time. We got another 10 minutes for the first half of class. Differentiate, yeah, let's see. This one is the chain rule. Let me write it out because I feel like I'm trying to do it in the little box. Too much.
Okay. Somebody, they said some people are in the waiting room.
What'd you say?
They said somebody texted in the chat that people are waiting in the waiting room.
Okay, I'll get them.
All right.
You, my friend, go here. Come on. I'm coming. All right. And let's get rid of that. Come on. Come on. Thank you. Do for right now. And then let's hop over here. Do-do-do-do. Okay. We probably got to do edit. Okay. Let's see who we got. All right. All right. There's one. And let's go ahead and let the one in too. Cool. That's fine. Let him in. Save. Come on. Record attendance. This class. Today is here. Next. Cool. Okay. All right. So let's see the next one. Oh yeah, we were working. So let's hop back over here. So we actually differentiate, right? So this one we're doing like it's the chain rule and it's like about 3 different like techniques in one, right? So when we go to differentiate, our dy by dx or y prime, whatever. Now, one thing I want you to notice is that we can rewrite this original. We have square root of this radicand. This is the same as the radicand to the power of what? 1/2, right? So now in this form, instead of writing it as a radical, we wrote it as a rational exponent. In this form, it's much easier to differentiate. So now we're basically doing the chain rule, right? The chain rule says the derivative of the outside function times the derivative of the inside function. In that example that we just did a moment ago, where the question popped up about the 4, that's actually the chain rule applied to the derivative of exponential base e, right? It was the chain rule is where that extra 4 came from. Derivative of the outside function times the derivative of the inside function. So that's essentially what we're doing here is the chain rule. So the outside function has that 1/2. So the 1/2 comes down, right? So the 1/2 comes down, e to the x plus 15. 1/2 minus 1 gives us a negative 1/2, right? Now we got to say times the derivative of the inside function. Derivative of e is itself, right? The derivative of a constant is 0. So then this is the only thing that's there. And then we don't want a negative exponent and we don't want negative exponents or a rational exponent generally. So I'm just going to rewrite this answer. On bottom, we're going to have 2 times the square root of e to the x plus 15. I think that's everything on bottom. And then on top, I think all we have is the e to the x. E to the x, all right? So let's see how do we do on this one. Feel good with that. And a lot of this is just experience. I know at first it might be kind of jarring. You just got to kind of work the system a little bit, right? Like we're doing remote, so it's okay. Like I just want you guys to be practicing. I just don't want you to get caught slipping. Like once, I'm just trying to prepare you. Not that you're going to be using this stuff verbatim. You may or may not. These are just like building blocks, right? But I encourage you all to work together, get it done, link up with the tutors that you've already paid for. Use your resources. It's totally like you just need to know how to do it. That's the main thing. So when you get out on your own, you can be doing this stuff and you can keep it moving. You're not going to let this stuff get in your way. That's the real intent of all of this. Okay, let's see how do we do. What is that? Where did it come from? I think that's work. I don't even know what that is.
Can I ask a question?
Give me just a moment. Let me see we got this one corrected, and then we can go from there. On top, we got e to the power of x, that's not x, and then on bottom, we got 2 square root e to the power of x plus 15. Let me see, how do we do? Okay, go ahead.
You was working the problem. I kind of got lost when you got the negative a half exponent. What made you get a negative half exponent when you multiply
Okay.
by
So you mean like this negative
yeah, right there. What caused
right here,
yeah.
right? So when we do the chain rule, right? Like for instance, if we had x to the power of 1/2, and we take the derivative of that, we do d by. If we take the derivative of that, remember the exponent goes in front, and we subtract 1,
Mhm.
right? So it's the same thing here. You got these parentheses. You just got to think about that as one thing. We got something. We got something to the power of a half. So we do the same thing. The 1/2 comes down in front, and we subtract 1.
Oh, okay. So in parentheses, yeah, you just move that, act like it's not even.
And we subtract 1. So you see the half here that's in front. 1/2 minus 1. That's where the negative came from.
Right, because it'll still just be a negative half. Yeah. Okay.
Yeah. Okay. These are good. And like,
Why did you so then why did you multiply e to the power of x now?
okay. So the chain rule says what? It's a derivative of the outside function. So we kind of talked about that already. Then we have to say times the derivative of the inside function, right? So first we did the outside, we got this answer. Then we say times the derivative of the inside. Now, if we focus on the inside,
right,
the first term is e to the x, right? So the derivative of e to the x is itself. So that's where this came from, right? That's what we talked about last class. The derivative of e is itself. And then we said plus the derivative of a constant. What's the derivative of a constant?
0.
0, right? So then it was e plus 0, so that's why it was just e. And then the negative exponent, it basically moved everything in its parentheses to the bottom. And that 2 was already in the bottom. So that's why it's like that. And this persisted on top.
All right, appreciate that.
Yep, pleasure. These are good. I'm glad you guys are starting to speak up, because closed mouth don't get fed. You know, you have to talk. That's what, honestly, whoever does the most talking does the most learning. I'm just filling the space until I'm really waiting for you guys by talking. Okay, this one we need to talk about. Let me see. Let's go like this. So I think this section is on derivatives of natural log. I'm glad we got to this one. Come on. Let's do one more. Okay, I feel like that's good. Let's get a copy of this guy. And let's do a little bit of a discussion on this, because I think this is the first one that we did where we're actually taking a derivative of the natural log. So we kind of talked about derivative of exponential base e. So now we're going to talk about the derivative of log base e. Log base e is natural log, right? So let's see. Let's talk about this. Let me think what other things I need to say. What was the reasoning behind that? Can I give a good reason? Okay. So the whole point is, I was trying to think of a articulate way. And you could verify it with the whole limit definition, but I'm pretty sure most people are not going to do that. But the whole point is that the derivative of natural log is 1 over x, right? Let me just kind of, and that's like the introduction. There's a little bit more, but we'll talk about that momentarily. So d by dx, the derivative of natural log of x, right now is going to be 1 over x. Okay. So with this one, When we go to find the derivative, in other words, our dy by dx, I'm going to use I think the quotient rule is fine. Low d high minus high d low. So then we're going to say the bottom, which is this guy, times the derivative of the top. So right there in purple, the derivative of natural log is 1 over x. So the bottom times the derivative of the top minus the top, which is this guy, times the derivative of the bottom. So x to the power of 11, the 11 comes down, and subtract 1, we get a 10, right? So that's low d high minus high d low over low low, which is going to be this guy. 22, right? Okay. I think let's simplify this down. We can simplify this down. Let me see. Both of the terms on top, we got an x to the 11 divided by x. They both have that x to the power 10, right? So we can factor out an x to the power 10. Halfway, okay. I think I'm gonna do one more from this section and then we'll go on to 2.4. So if we factor out x to the 10, let me see. This combines with this to give us x to the 10. So if we remove x to the 10, that means that there's a 1 left over there. Minus, we factored out the x to the 10 from there. So then what's left is 11 times the natural log of x, okay? Now, we could move this to the exponent. I'm gonna check something really quickly to see what form would they like us to leave that in. And then on bottom, I think the x22 persists, right? So if we have x to the 10 divided by x to the 22, you subtract, what is that, 12, right? So basically what's happening is this 10 is turning this 22 into a 12. You subtract, right? So then what's left over, 1 minus 11 times the natural log of x over x to the power of 12. Okay. I want to check the viewing example to see what form, if this form is similar to what they did, and then I will submit it. So I'm just going to go like this. Okay. Let's go to view an example. Let's see. They did the low d high minus high d low. So it looks very similar. Oh, I went too far. View an example right here. Let's stop at the end this time. Okay. So yeah, they got something similar, right? So let's submit our result. I'm confident in our result. All right. Let's go like this. Let's zoom out. It's a little bit far. Okay. All right. So we got a fraction. 1 minus 11 natural log of x over x to the power of 12. Cross your fingers. Awesome sauce. Okay. All right. So let's do one more from this section and then we'll move on to section 2.4. Do one more. Let's see if we can get something a little bit more interesting. The demand, blah, 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 can give with this, in dollars, number of games sold, 1,000 recalled, the revenues, complete parts A through C. That's a little bit longer than I want to do right now. Oh, and that's the last one? Okay. Yeah, I don't want to, because I don't want to infringe. I don't want to go eat into so much of the time for section 2.4. Let's do this one. Okay, I think we got through just about all of these guys, nearly. I think there's at least one more. All right. Okay. 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 tempted to try this at the bottom now because it's kind of irking me at the top of the screen. Okay, differentiate, right? So now with this one, we can apply the properties of logs, all right? So I think there's a property that says the log of a quotient is the same as the difference of the logs, right? That might happen, that's okay. So we can rewrite this. This is the same as the log of x to the 9 minus 11 minus the log of x, right? Yeah, so this is a good one, right? So we kind of when we introduced the derivative of natural log, we said it was 1 over x. So now with this one, to extend it a little bit further, is basically the chain rule again, right? So it's still going to be 1 over this thing, but then we got to say times the derivative of this thing. So the derivative of natural log is going to be 1, is basically going to be the derivative of this divided by that, divided by itself, right? Let's see it in action. So then f prime, on top, we're going to have the derivative, which is going to be, in this case, is going to be 9x squared. Again, derivative of that negative 11 is a constant over itself, which is x to the 9 minus 11. Okay, that's the first one. And then the derivative of natural log of x was 1 over x. We're going to say minus 1 over x. Okay. We could combine these into one fraction. I am going to use my resources and see how do they submit it. Because I mean, this should be fine as is, but sometimes they want to go further. So what I'm going to do is just match. Like if they go further, then I'll go further, right? You know, we don't have to spend too much time. Oh, okay. So we don't have that option here. Let me think. Let me try submitting this first. If they mark it wrong, I'll combine it into one fraction and take it a little bit further. I'm pretty sure that's what they want us to do, but sometimes you don't have to do it. So I'm just going to try 9x squared, right? And then we got x to the power of 9 minus 11. And then we're going to say minus 1 over x. Okay, let's see what they did. And okay, so what I'm going to do is extend it, like simplify it down some, extend it a little bit further. So if we get a common denominator, right? If we're going to get a common denominator, let's get rid of this too. So common denominator. For this first one, we're going to multiply by 1 in the form of x over x. So we get our desired denominator. And the second one, we're going to multiply by 1 in the form of x to the power of 9 minus 11 over x to the 9 minus 11, right? So again, we're just multiplying by 1 so in a form so that we can get a common denominator. So then if we account for these changes, first we get 9x cubed. We distribute that negative. Is that okay? Oh, wait a minute. Okay. That should be a 10, right? X to the 9, that should be an 8. So that's one thing. So we definitely had the wrong answer. This should be x to the 8. Let me do that in red. This should have been x to the 8. So let me go back to the answer that I had and change the square to an 8 and see if that works. We might not need to combine this. We just need to change the square to an 8 right here. Change it to an 8. Let's see if this works. Okay, cool. See, I was like, I felt like we didn't need to simplify, but we had the wrong answer, right? So we had took the derivative incorrectly, but we adjusted, we found it, we fixed it, we kept it moving. Let me update my notes really quickly, and then let's hop to the next section. So we didn't need this, delete. We don't need this, delete. We don't need this. And we can put this back. And I left the change, the thing that I changed, I left it in red. All right, so we can, because we definitely missed it. Okay, so now from there, let's hop into section 2.4. So I'm going to close this out. Do I need to like go back? I guess I need to go back to assignments. Allow. So this is week 4, right here, 2.4 applications of the growth models. Okay. And we'll get through as many questions as we can. We got a good amount of time. We have enough time. Okay. Let's go like this for right now. Can we zoom in some? Okay, that's fine. That's fine for now. It says use the graph of E and transformations to sketch the exponential function that you see here. Determine the domain and range, and also determine the y-intercept and find the equation of the horizontal asymptote. Okay, let me zoom out some. Oh, nope, I hit the wrong button. Darn it. We're probably gonna get a different one, but that's okay. We hadn't started yet, so. Okay, let me zoom out one more. Okay, we're gonna click to enlarge the graph. Now, the base function is exponential, right? So that's in this, and for these options, that's going to be in the upper right-hand corner. So I'm going to click the exponential, and I'm just clicking anywhere on the graph, right? So then basically what it wants us to do is to list out the transformations. So this -5, that -5 that you see there, kind of in the center of the screen, that -5 is outside of our base function, right? It's not up there next to the x, it's outside. So it's like subtracting 5 from your y values, right? So outside manipulations generally cause a vertical change. These are transformations from college algebra. That should shift the entire graph down by 5, right? So vertical shift down by 5, right? And that should be it. So for instance, when x is -4, well, we can't see it. Sorry, when x is 0, we should get a result of -4. So e to the 0 is 1. 1 minus 5 is -4. All right, that's so you can check a few points like that. I'm gonna go with this. This looks good. Let's hit save. That looks good. Let's check. Okay. What's the domain, right? So this is our graph. In a graphical sense, the domain is going to be the very left to the very right. So the far left is what? Negative infinity. I feel kind of bad because I feel like the upstairs neighbors heard me talking about them during my lectures. And I feel like they may have stopped, or this just might not be one of their workout days. You know, who knows? I might be full of myself. The far left is what? Negative infinity, right? And the far right is actually positive infinity. It looks like it might cut off as you go to the right, but actually, no matter how far right you go, you can find the corresponding y. So with exponential graphs, we have a horizontal asymptote that we don't cross, but there's no vertical asymptote for exponentials, right? So the domain is all reals, negative infinity to infinity, okay? The range, so if the domain is the very left to the very right, the range is the very bottom to the very top, right? The range is the very bottom to the very top. So with exponential graphs, we have a horizontal asymptote that we don't cross. So it looks like the graph touches the line of y equals to -5, but in actuality, what it is that y equals -5, and for this specific example, is a horizontal asymptote, which means we get infinitesimally close to it, but it actually doesn't touch it. If we were like Ant-Man from Marvel and we were to zoom in where it looks like it's touching, we're actually going to find space, right? That's not something that you would know. Someone would have to bring that to your attention that exponentials have an asymptote and there's always space between our line and that asymptote, right? So with that being said, the range is going to be the very bottom to the very top. So now the very bottom in this case is going to be -5 up, and the very top is going to be positive infinity. Infinity always gets parentheses, right? Because we never reach it. And in this one, as far as the grouping, we had to decide, okay, is it parentheses or is it square bracket? Parentheses mean we get really, really, really close to that thing, but we never reach it. Square bracket means we get really, really, really close to that thing and we do reach it, right? So if you never had this conversation with anybody, looking at it, you might be tempted to put a square bracket, but in actuality, this one is a parentheses because it's an asymptote. We actually never reach it, all right? So we're gonna go with that. And I intentionally was just giving you backstory and some of the concepts behind this, some of the stuff I said in the lecture, just assuming that many people probably are not watching it. So I try to get as much of the lecture as I can out in this. I did want to kind of get to applications. I mean, I think we're okay. This is fine. The y-intercept, so that's when x is 0, the y-intercept is -4. I'm just going to put -4. Okay. Horizontal asymptote is y equals -5. Okay. Okay, let me hop to a question that's from section 2.4. That's 1.2, so that's a little bit of review. 2.4, okay. Find the general form of the function that satisfies this. Okay. So let me do it like this. I'm trying to I don't want to give too much of the backstory for this. Okay, so this is a special case that came out in the notes. And there's only one function, there's only one type of function that satisfies, where basically you take the derivative, and when you take the derivative of the function, you get a constant times the original function, right? There's only one function that does that. And we talked about it in the notes, and I think that's enough of a backstory for that one, and I'll just show you what that function is. Let me get a copy. Let's go here. Okay, cool. Right there. Cool. That's fine. Come on. Go here. That's good about there. Okay. So again, there's only one function that satisfies this, where you take the derivative and your answer is going to be a constant times the original function. That's essentially the exponential growth model. So we're gonna take one of the form a of t equals, let me think about it. It should be a naught e. Find the general. I feel like I might be missing something. KT, something like that. Where a naught are like your initial conditions, and k is the rate. Find the general form of a function that satisfies this. Let's see. Do we have enough information? There's something else that I'm missing. Let me think about it. Okay, yeah, there's a little bit more. Let me think one more time. Because that's a constant, right? Is it 5 times your original? Maybe the -5 needs to go there. There's a little bit more to the story. Let me hop over here. Oh, we don't have that? Okay. I'm tempted to pull up the notes from this, because I know I have it in the notes. A of t, right? We're not doing integrals. And I think that that -5 might be our k. If we make k -5, right? Okay, so then at that point, do we get another point or anything? We could say -5 e to the -5t. I think, okay, I'm gonna call for my own resource, and I'm gonna pull up the notes from that section. 2.4, I think is this one where we worked it together. Right here, it's the first thing. Right here. All right. Here it is. Find the general form of a function like this, right? So by theorem 9, let's see. Yeah, that's what we got. We got that. So then A is going to be C e to the, yeah, that's what we got. Okay. Oh, that's it? Okay. Yeah, I was just thinking that we needed that K. I guess we can just let K be 1, right? And we're good to go. So what we have is fine. We're here. This one, right? So then let K be -5. So let's see here. Find the general form. So then we can say A of t is going to be some starting amount, or we might let it be 1, e to the 5t, right? And so all we would do to check is we would take the derivative. So when we take the derivative of this, again, the a naught is just some number, it's a constant, we're probably gonna let it be 1. And then the derivative of e is itself times the derivative of the exponent, so times the -5, right? And so I think for this one, just let the initial, I'm just gonna call it audible. I'm gonna say let a naught equal 1 in this case, right? We're just letting the initial conditions be 1. Okay, let's try that where we let a naught be 1, and let's go with that. Let's hop here. Like this. And let's see what happens. Okay. Does it say anything about the rate? Can we solve for it? Let me think real quick. That derivative is going to be -5 times that. Yeah. Yeah, I think even if you like equate them, you get the a naught as 1. I'm just going to go with this. So then we're going to have e to the power of -5t. I think that's okay. Let me see. A function satisfies blah, 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 if and only if, and where c is a constant. So I think we need to solve for that constant. Okay, so if we're going to solve for that constant, then let's do this. So the constant is a naught in this case. But if we're going to solve for that, let me see. It says that the derivative is -5a, right? So the dA by dt, the -5 comes down, it's going to be -5 times a naught e to the -5t, right? I'm trying to think. If we let this equal -5 times this, isn't that a repeat? And that's a 1. Oh, duh. Okay. I see what it is. I see what I did wrong. I don't think we typed an equation. No, they got it. Oh, maybe we need to just put C. Let me see. I feel like this one is just a form. Like, I don't think we're missing anything. I think we just gotta get it in the proper form. C e to the -5t. I feel like it's some kind of small something. Okay, let's try this. Yeah, it was a C. Because like I tried to solve for it. I thought, let me get rid of that and let the A1. So it wasn't that. Like this. We're gonna get rid of this. And I think we got it pretty much from the rip. We just had to get the proper form. All right, because and another reason I was hesitating, I was like, well, in order to solve for that constant, we need another piece of information. Right, that's where my hesitation was coming in. I was like, well, we don't have any more information, so what's that constant? Right, but we got to the bottom, so we just didn't even solve for the constant. We just left it. Right, that's the thing that, because I was looking for another piece of information like a point or something like that. But let's just do another one. Let's just try another one. We're actually no more than 10 minutes, right? Let's just hang out for another 10 minutes. Let me see. So in 2004, an art collector paid $141 million for a particular painting. The same painting sold for 141. Really? The same painting sold for $31,000 in 1950. Okay. I was like, usually it goes up, but we went backwards. It was weird how they did that. Complete parts A through D. Find the exponential growth rate to 3 decimal places and determine the exponential growth function. Let me see something. Okay, that's at least there. Okay, find the exponential growth rate. Okay. I kind of need to go back and forth. Yeah. So let's go like this. Hopefully it won't be too terribly jammed. So exponential, this is what question? I don't like the way that looks. Come on. So this is the first part. Time for dinner. Boom, 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 boom. Oh, come on, right here. And we'll kind of work with this for now, and I'll just pull the other parts as they rise. Okay. Well, we need part A. I thought we had it. Okay, find the exponential growth rate K for three decimal places and determine the exponential growth function V, which is the pain's value in T years time. Let me get a copy of this. Oop, what did I hit? We are here. We need all of this. This will probably be the last one. This has several parts. I'm going to drop it right here. Okay. So find the exponential growth rate. So that means it sounds like we're using, we want the value based on time. It's just an exponential growth model. I like to call it V naught. That just means the initial conditions, e to the kt, right? Let's see, it says in 2004, it says in T years after 1950. I'm assuming that 1950 is our starting year. Let me see. Because I know one of them, we had to use the negative. Complete parts. It says find the exponential growth rate to three decimal places and determine the exponential growth function for which this painting in years after 1950. Okay, I'm gonna take a chance and I'm gonna let 1950 be year zero. I know there was one where we kind of worked backwards, so I'm just gonna, because it says years after 1950, so I'm gonna let that be my year zero, right? So then if we get like an ordered pair from this, I'm gonna let 1950 be zero, right? That's gonna be our zero. So at that time, it sold for 31,000, right? That's in 1950. Then in 2004, how many years later is that? 50 will be what, 2000? So 54 years later, it sold for, man, 141,208,000. Okay. Okay, this might work. So now let's plug in the first order pair. If we let 1950 be year zero, right? So then the value at the start, we don't know. Well, that just means, okay. So that value was what, 131,000. If we plug in t equals 0, this term collapses to 1, right? E to the power of 0 is 1. So then that 31,000 is our V naught, or our the initial price of the painting, or value of the painting, right? So then we can take this. Now, if we want the value 54 years later, that's going to be the 31,000 times E. The T in that one is 54. So then we got K to 54 times K. Okay. So all I did for the first one, I plugged in T was 0. This term collapses to 1. E to the power of 0 is 1. So that means that V naught equals 31,000. So then I took that. This became 31. Now the time is 54. Only thing we don't know is K. So we can solve for K. All right, we have everything except the rate. So then we have this value model equals 141,208. Right. So then from here, it's just algebra. Divide by 31. So we get e to the 54k. You get your 141,208 over 31,000. Now, to get those expressions out of the exponent, we take the natural log on both sides. So natural log of this, we're going to take the natural log of this. These cancel, and that comes out of the exponent when we do that. All right. So then on the left, we're going to have 54k. On the right, we have this 141,208, 123, divided by 31, 123. We got the natural log of that, right? We're just letting that persist. And then we got to say that entire expression divided by 54. Okay. So then ultimately we get k equals, let me just copy and paste. Copy, paste. We can either do it like this and divide by 54, or that's going to be the same as multiplying by 1 over 54. I think I'd rather do this, 1 over 54, right? Dividing by 54 is the same as multiplying like this. So this will give us k. So then let's take this, we're going to plug it into our calculator. Oh, we are just about out of time. Let me pull up my trusty dusty rusty. So what I'm gonna do is go here. I want to pull up the calculator right here. And I'm gonna just pull that over to the side. And even take it a little step further, like this. Reload, come on, and refresh. Okay, I think that's okay. All right. All right. Oh, shoot. We need this guy. Okay. So in the times, now we have the natural log here. Let's do this because we don't need that extra one. We can do the natural log. Now on top, let me think about this. Parentheses. We got 141,208, 123 divided by 31, 1, 2, 3. We need to close off the log. That's the main one, okay? So then it should be positive. We got a growth rate, almost 15%. So then what we're gonna do is hop back over here. And submit that result. Type an expression, type an integer to 3 decimal places. Okay. So they want us to plug that in for k. So our initial conditions, we got 31, 123 times e to the power of our k, which is 0.156 times t, right? Now, we could check that this function works before we submit it. Yeah, let's put a 0 in there just to make it a little more clear. So before I submit this, I'm watching the clock. I'm trying to get you guys out of here. I'm going to check. Again, this is all based on 1950 being year 0. So I'm going to say times e to the power of 0.156. Was the 6 correct? Times t, I'm calling it x. I'm going to hit enter. I'm going to quit. Yeah, 156 was fine. So I'm just going to call up that function that I just typed. If you need to know these keystrokes, let me know. Now, in 1950, that was the year 0, we should get 31,000. And then 54 years later, we should get our 141, blah, 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 blah. So if we change 0 to 54, 141, oh, we got a little bit of rounding. The rounding is fine. That's about the best we can do. Stop. Okay. So let's go with this. And let's see what happens. Type integers or decimals, round to 3 decimal places. Okay. So now that we have our model, predicted value in 2028. So if 2004 was 54, 20 years later will be 2024. So 24 years later, 54, 74, 78. So then we need to take our model and put in, I think it's 78. 78, okay. Nearest million. Let me see. Okay, I'm gonna have to, let me see. 1, 2, 3, 1, 2, 3. Okay, I can't really see it. So I'm gonna do like this. 59, 68. I'm gonna come back and redo this. 38, 66, 41, 66, 41. Right, now if I introduce my commas, come on. Let me suppress that. I'm trying to get you guys out of here. I see the time, but I would like to at least finish this one. Come on. Okay, let me see if I do. Okay. So I'm just trying to see my commas so I can see it better. It said the nearest million, right? So this is 1,000, million, that's billion. So the nearest million looks like it's the 8. So I'm just gonna change all these to zeros. 1, 2, 3, 1, 2, 3. Okay. Estimate the rate of change in 2028 to the nearest million. So the derivative, right? Let me see. So for our function, we need to kind of like take the derivative. So the derivative of this is going to be what? Itself times that rate. So all we got to do is basically take our previous answer and multiply by that rate, that whatever the rate is, right? So that's what I'm gonna do. I am trying to be, let me see if I go like this. Okay. So then for the next one, all I'm gonna do is say that answer, I'm gonna say times, I think the rate was 0.156 times 0.156, the rate of change. Okay, that's per year. Okay, so let's do years per dollar, dollars per year. Come on. I see the clock. I'm about to let you guys go. And this is being temperamental. Here, let's put you here. So you're kind of blocking my way. Okay. And then this. Let me zoom out. Okay. So now I got this 93, 10. I got 68, 316, right? It says round to the nearest million. So I'm going to put my commas in there so I can see it. So that's 1,000 million. It says to the nearest million. So we would stay at the 1. So I'm going to change these to zeros. 1, 2, 3, 1, 2, 3. So what we're saying is that it's increasing by nearly $1 billion every year. I feel good with this. Let's go with this answer. Okay. Is that the last one? I think there's one more. Yeesh. How long after 1950 would the value of the painting be $4 billion, right? So basically they're saying set Y equal to 4 billion and solve for T. Okay. So our model, we never wrote it there, but we got it. Let me see if we can solve it. I'm going to try to do it. We got, let's see, we got V of T, 31, 1, 2, 3, e to the 0.156 T. We want to know when will that be $4 billion, right? So I'm just going to set it equal to 4, and I just got to keep in mind that that's in terms of billions. Okay. So then if we want to solve for T here, let's just go ahead and do it. So then we get e to the 0.156 T equals, let me write the billion, that's 1,000, that's million, that's billion, all right? Divided by 31,000. And then to get that out of the exponent, you take the natural log on both sides, so we'll get 156T we're going to have the natural log of that 4 billion, that's 1,000, million, billion, over this, natural log of all of that. And then we got to say that, so then ultimately T is going to be that divided by 0.156. Okay. That's the exact result. I think this is it. I know, I see the time. Let me just do here. Not that one, this one. And if we're gonna do the natural log on top, we got 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, divided by 31, 1, 2, 3, okay? And then we say all of that divided by 0.156, okay? 4 billion, right? Okay. So 75, we get 75.4347 years since 1950. Okay. So then we're gonna hop back over here. Nope. Like this, full screen. And okay. All right. How long? It says do not round until the final answer, then round to the nearest year. The nearest year is 75 years later. Okay. So they give specific instructions. This is it. I just need to submit this and we can go. We can let my people go. Oh, come on. Right there. Okay. We're going to put 75, cross our fingers. God is good. Okay. All right. We went over by 2 or 3 minutes. Okay. So what we made it. Okay. Okay. Drugs are bad. Okay. But 75 years later, right? Through as much of what, 2.3 and 2.4. So those are the 4 sections for this week. I think one of those assignments we got through all the questions, shy of 1, right? So if there aren't any burning questions, we're going to end the session here, and from one beautiful mind to another.
Professor,
Go ahead.
Class when everybody leaves.
Do you want this streamed or not streamed?
Not streamed.
Okay. Are there any questions that are okay to go on the stream for everybody to hear? If not, let me go ahead and end the stream and I'll be right with you. Okay, stop. And then stop the stream.